paper has a focus on BMI, which I think we all have a rough idea what it is. But the main point about the paper is not so much about modeling BMI. Of course, that's important, and we'll go through some of those examples in a minute. But it's also about the techniques that we apply. So this is essentially applying a woolly old concept in statistics, specifically in information theory, and try to put some new tricks to it. And this is the kind of work I have been doing in another context for a very long time, for about 6-7 years now. So we're going to talk, we basically take this in a slightly different directions, and we're just applying to BMI to see what it will get us. So we're not saying we solve the world problem. We certainly nowhere near that. And what we're hoping to be able to do, however, is to add another two sets into your toolbox in terms of data analysis. So it has its strengths and its weaknesses, and we'll go through some of that in a minute. So basically, we're going back to BMI. So my point is the BMI is not really it is the focus in this particular presentation, but the whole point about the paper is not just about BMI. I have to qualify that because when we used to present this paper to a bunch of health economists, we got jumped in the first 5 minutes saying that, oh, nobody cares about BMI. It's not a good health indicator. Why you bother doing that? So I thought I'll mention that up front. So these techniques can apply equally to other health measures where appropriate. So, so going back to BMI, so it's a measure of sort of estimate individual body fat. As I mentioned before, it doesn't really achieve that very well, but it does give you some information. So the basic measurement of BMI is basically your weight divided by your height. The idea is proportionally your mass should be proportional to your height if you are relatively healthy. So in the measure of BMI, it's a simple formula, your weight measured in kilogram divided by your height measured in meters squared. Now, so the classification, which is not ours, is sort of imposed by policymaker like the World Health Organization and the rest. Basically, they have the consensus that if your body weight is below 18, then you're underweight. If it's somewhere between 18 and 25, you're relatively normal. If it's somewhere between 25 to 30, you're overweight, which is why I am. And if you're above 30, then you're obese. Now, I wouldn't say that threshold, that classification is purely arbitrary, but in some sense, you've got to ask the question: how did they come up with those thresholds? So that's the first attack we've often got. But we're going to take those thresholds, those definitions as given. So obviously it has limitation. My colleagues there, Mark Harris, he's about 10 years older than I am, and he's a mad gym goer. So he will go, he got muscle like his arm is the size of my leg. So those guys, obviously, if you measure the BMI, he's actually in the obese category, which upset him greatly, right? Because I was overweight and he's actually obese. And he goes to the gym like, 6 times a week. So this sort of highlights the limitation of BMI. We all know, well, you guys scientists, we know better than I do, muscle weighs more than mass, than fat. So, if you're one of those muscly guy, chances are you're going to be either overweight or obese, even though you're probably healthier than most of us. Okay, so here's the limitation and qualification, but nevertheless, the fact of the matter is BMI is one of those things that being used a lot. It's like value at risk in finance. Everybody knows it's a crappy risk measure, but everybody uses it. So it sort of becomes important. The importance not because it's a good measure, importance because people rely on it. So we're not going to go into that debate. We just put it down as organization uses BMI, and policymaker make their policy based on BMI. So we're just going to have a look and see what that variable looks like and how they behave. And of course, it has impact on society. We have recent news about obesity being one of those endemics that face Australia and the US. And basically what we mean, though, what's interesting about this is, just jumping ahead a little bit, when we model something, our natural instinct is to model the mean. Whereas what we really cares about in this case is the tail, right? Nobody really cares if you're in that 18 to 25 category, you are healthy. As far as government is concerned, you pay your own taxes, we don't care. What really is going to cost the government in some cases are those who are over 30. So it's in the tail of the distribution. So this is the kind of things we're trying to get to. So we're going to break away from the traditional modeling and try to look into the different characteristic of the distribution other than just the old boring moment, first moment. Of course, we're not the only person doing that. We don't claim to be the first of doing that at all. There's a whole health econometrics literature on BMI. So this is a very limited, and I could not emphasize that enough, it's a very limited. So if I offended anyone here who has done any BMI work and your name is not on the board, my sincere apology. It's really just a sample, very small sample. So here is the, and what we did here is basically looking at the literature and divide the, we focus on the methodology and divide those paper into two groups. The first group basically focuses on modeling the distribution, but they are sort of unconditional distribution in the sense that they're only just looking at a snapshot of a population or sample and look at that overall distribution of BMI. Nothing wrong with that, but what it does means is it's less likely to be helpful for policymakers because we really want to know whether it's your diet, your education, your gender, your weight, your income, or any sort of socioeconomic factors that affect your BMI or your health indicator. So those guys did and of course those are not the purpose of those papers, but just looking at it from a policy viewpoint, those papers are nice. So you got Pamela and Johnson suggesting using a log normal. Lin et al., Lin himself is quite a renowned statistician working in the area of skill normal density. So he has a really nice paper covering mixture of basically skill normal, skill T, mixture of normal, mixture of skill T, mixture of normal, did the whole lot. And it basically tells you that the mixture of skill T seems to fit the distribution the best, which is nice. Kotoyanis and Wyman propose a sequence of non-parametric techniques, estimated non-parametric density, and then it has a whole pile of techniques to compare and see which one fits better. So, so the last paper focused more on non-parametric manner, just trying to cover the scope with people from parametrics and non-parametric working on this. So the second group of people focus on the issue I mentioned earlier. They're more concerned about how the different variables out there can affect the BMI. But they focus more on the mean and the medians, which as far as the tail is concerned is a bit lacking in terms of information. So a really nice paper by Anani. He did the mean, but I guess in his case is quite different in the sense that he also applied quantile regression, looking at the specific quantile of the distribution and see how those different covariates like your income, your gender, your education affects the quantile of the BMI. So that's the closest we can find to what we really want to achieve. But of course, when you're doing that, you have to do one quantile at a time. So it doesn't say too much about your entire distribution rather than just a particular percentile or particular region of your distribution. And in some sense, that might be enough. So we're not criticizing it, just saying that this is the kind of things they did. So one of the closest one to what we managed to, what we are trying to achieve in this paper is Brown et al., Sarah Brown, also Mark Harris, and William Green, Bill Green, a quite well-known econometrician. So one of our co-author, and is in some sense, the application to BMI was arises because I was talking to Mark about this particular paper of his. And then it just dawned on me, maybe we can try something different. So what they did in that paper is they essentially has a mixture of distribution. So the idea here is BMI consists of different distribution, and you weight those distribution based on some sort of probability, which is what a standard mixture model is. Except in his case, his twist is that the probability on each of those random variable is governed by a set of covariates. So basically, you can think of that as you have the underweight random variable, you have the normal random variable, you have your overweight, and then you have your obese random variable. And which group you're going to belong depends on your education, your income, and the rest of it. So it's kind of nicely the twist to that, and it's very, very close to what we're about to propose. So what we're about to propose is actually the complements to that techniques. And one of the future work that we're going to do is actually comparing both, to see what information in its totality we can get and see if we can actually improve anything from it. So, so the emphasis, you probably get that by now. What we aim to do is model the distribution of BMI, not just one particular moment, using information from the covariate. And the things that we're looking at in this particular case is how we're going to use a different covariate or look at how the covariates or explanatory variables, whatever you want to call those things, affect the different moments of distribution. Because we know when a moment exists, the moment says everything we want to know about a distribution and vice versa. Okay, so the basic idea comes really, really old. This back in the Shannon day, just after the Second World War, as the information is the father of information theory, and he proposed this little mathematical problem, which is known in the literature for even longer. And basically, his idea is try to maximize the randomness in a system subject to what we know about the system. So what we know here is, so he has this what we call the Shannon entropy. He tries to maximize as an objective function subject to a bunch of constraints. And the F in here is the density, the unknown density of a particular random variable. And the constraint is that obviously the density has to sum to 1, and that the high moment is equal to a specific value given. And so this is a nice little mathematical problem, go back eons ago. And the idea basically is if I give you a sequence of moment, right? If I give you a sequence of mean, variance, skewness, kurtosis, and so forth, can you then tell me what that distribution actually looks like, right? But I don't give you infinite moment, right? Because if you've got the moment generating function, that's not really an issue. But if I just give you up to, say, the first 6 moments, can you still tell me something about the distribution? Right, so that was the idea of it, and if you solve this little mathematical problem, you'll get a solution. This is sort of famous. The Q is a normalizing constant, just to make sure that your first constraint, that the integration of density is equal to 1, and the idea is this particular functional form, which end up is in a sense a generalized exponential distribution. The only thing that I will stand out is that to say is that the lambda is a Lagrange multiplier, because essentially this is a constraint optimization problem. So the lambda basically carries all the information about your moment. So basically deriving this or actually estimating this, right? In one way of looking at it, it becomes a nonlinear transform between your moment and this lambda. So they are essentially the same thing. So the lambda carry the same set of information as all your moment constraints. So this is where the information comes in to determine the size and the scale and the shape of your distribution. Now, this is all really nicely presented. You can find any paper on maximum entropy. You will see this derivation. One thing they didn't really tell you is whether you actually get the lambda, whether your problem is solvable. And when we say the problem is solvable, is whether you can actually derive the lambda or estimate the lambda. It actually depends on this moment constraint. So you can't just randomly give me a sequence of number and call them moments and say, can you back out a density for me? It would be the case that if you give me a sequence of number and this lambda doesn't exist, right? So this problem is called classical moment problems. It's been around in the literature for donkey years. And a lot of people has been working on it for quite some time. Lucky for us, we don't have to worry about that because in our particular case, these two guys, Frontini and Talignani, especially Talignani, has done an awful lot of work in the theoretical backbone and this sort of thing. So he has a whole set of condition to ensure, has a whole set of condition on the sequence of numbers to ensure this little lambda stuff, this Lagrange multiplier actually exists. There's also some limited work done on, okay, so you can say, give me the mu, I can work out what lambda it is for you. Is that solution unique? Those work has also been, has a lot of progress in the last 20-odd years, 30 years, sorry, I can't do arithmetic in the morning. And mostly by Senna and Highfield, which is a signature paper in economics using this sort of distribution. Okay, so that's the backbone, right? So immediately you can see one of the nice things you can immediately do, naively looking at this, right, is to actually make this guy, because this is the moment. This is your mean, this is your variance, this is your skewness and kurtosis or whatever. You can actually make this depends on all the covariates, right? So that's the natural things to do. And in fact, that's what people did do. But before I introduce what people have done, I just want to give you a bit of an introduction and try to wake you guys up in case I haven't put you guys to sleep already, just to see how flexible this distribution is. So what I have here is a set of lambda. So these go up to 4. And what I want to show you is a little animation. Just tells you for different values of lambda, what sort of shape you can end up getting. So you can get something from a sort of like a normal distribution to a bimodal. And so if you look at this case here, you get something almost quite funky here. Normally, you wouldn't bother to estimate this with parametric. It probably goes straight into a non-parametric or mixture of normal. But this is a kind of shape. No, and also shaped like this. This is the kind of shape you will probably wouldn't dare to think of a distribution to use. And this is the kind of shape that the generalized exponential distribution can actually produce. So it's kind of neat, it's kind of cool. And I will claim my credit here. This animation is my only contribution to these slides. Renjon did all these slides for me. So thank you again. So this is the, again, this is just to show you how flexible the distribution we just look at with a fixed set of lambdas. So as I mentioned before, a natural way to incorporate information from covariates is to actually make the make the mu, the moments, depends on the covariates and solve the lambdas accordingly. And that's what Rockinger and Jordan did in the time series setting. Wu did some work in, so Rockinger and Jordan mostly look at financial application. Wu did a lot of work in that regard for income distribution. Park and Barrett also proposed a very similar structure, again in financial application. And Chen, this is me, I did some work in that. But the work that I did with that was actually the same trick that we're going to show here. We're abandoning mu. We're not actually put the information in mu. And the reason for that, we'll tell you in a minute. But the 2 points that we're trying to make here is that the lambda control the shape of the distribution, essentially. And we know that the lambda is also the function of mu, right? So if the shape of the distribution is what we're trying to get at, right, why don't we just model lambda? Why don't we just abandon mu? And then we work backwards to work out what it means to the moment. So, so this is the tag we do. The reason we don't want to do the put the information in the mu is because during the optimization, when you're doing maximum likelihood estimation, it means that you have to solve lambda every time when you're doing the integrations, because it means that if you put the information in mu, you have to go back to the original mathematical programming problem and solve for lambda every single time, and that slows down the process substantially. Whereas if you just model lambda as a function of covariate, you kind of a standard maximum likelihood problem. And almost any optimizer can do that. So just more from a computational efficiency, we're trying to see if that actually makes our life easier. So an example here is for each of those lambda, which depends on a set of covariates, your x, and your beta is your coefficients. And so we have a BMI distribution, so all we've done here is to write down the density conditional on x and replacing lambda with a linear function of all your explanatory variables. So beta is our matrix of parameters. So we still maintain that flexible functional form. Maximum likelihood, anything is a standard techniques. We can show that under certain conditions they are consistent. We got the result for asymptotic normality for the estimator. And we just haven't typed it up yet, and we need to check. In some sense, we spend a lot of time on this because we want to be able to do inference. So we try to work out the asymptotic distribution with the most relaxed set of assumptions. So proving asymptotic normality often is not difficult if you're making a lot of assumptions. So we spend a few months trying to relax those as much as we can. So we're getting there eventually. But from a policymaker perspective, stepping back in a bit of a real life, what they really want to know is, in some sense, is how does the covariance related to the moment? So the lambda is hard to interpret. So you can't, you got the shape, nice and everything, but you can't really interpret, if I change income, what does it mean? What does it mean to my average BMI? If I change my education, what does it mean to the variance of my BMI? So we also work out the marginal impact. So we have expressions here that we can evaluate that allow you to go back to the look at the marginal impact on how the changes in each of those explanatory variables can affect the different moments of the distribution. So that's our theory. So what we have here is a data. So we borrowed the data from household income labor dynamics. In Australia, it's a Hilter data set. I don't know many of you used this before, but apparently it's quite a famous and well-known data set. So it's a panel data set from 2001, 2012, and probably more now, actually. And so approximately, on average, 10,000 households with 26,000 individuals. And it has a lot of information on health, BMI, subjective well-being measure, employment status, family attributes, and so forth. So there is a lot of things we can use. So instead of attacking to the more complex panel data structure and deal with issues like fixed effects and individual homogeneity, all that sort of stuff, we took the very quick and dirty approach in this and just take a snapshot of 2006. We've got the individual height and weight, which means we can calculate their BMI, assuming that we plot that accurately. And we're just going to have a look at the BMI distribution for the sample in 2006. So if you just plot the histogram, this is roughly what you got. Here, 2012, nothing too sinister here. And in some sense, you can see, why don't you just do it with a log normal? And you probably could. But what we want to do is to apply our techniques to it. And we've got two decisions we need to make. The first one is how many moments we care about. So how many moments do we want to model up to? So obviously we want to mean the variance, but we also want to say something about the tail. So we have it up to the fourth moment. We can probably do more, but for experimental purpose, and as I say, this is very much we're still very much testing the water at the moment. So we just have it arbitrarily designed k equal to 4. Now, in the literature, there is a technique that allows you to see whether adding extra moment will actually add anything in terms of the shape of a distribution. And that's mostly from that Wu paper. He has a very nice test that allows you to see if keep adding extra moment, whether that will actually make your result any better. We didn't do that, and we probably should, and that is sort of one of the things on the to-do list. But we certainly have reasonably good result at 4, so we know, or we're confident, we don't know, we're confident that k equal to 4 is probably the minimum. Whether adding 5th, the 6th, and the 7th moment helps us, we'll leave it for future research. And the second thing is actually what goes into the X, so what's going to be in your experiential variables. So we don't know much in this literature, unfortunately. I'm not a health guy. As I say, I'm overweight. And Mark is not, he's basically said, well, he basically tells him whatever sensible you follow in. So that's not very helpful. So what we did is we go back to the literature and see what people use, those names that you have seen before. So we obviously have gender, socioeconomics, inequality, age, and ethnicity. From some people, and from how we have gender, ethnicity, and education. And so we cross-check what's the most common variable they use, and we just throw it in. So the choice we have, we estimate a few models. This turns out to be the one that we're the most happy with. I'll tell you what we mean by we're most happy with when I'm not being recorded. So we have the variables on log of age, how active you are, whether you marry or not, so whether you're the gender, male is a gender variables, log of household income, so basically is how your income affects your BMI, number of children you have, your employment status, 1 if you employ, 0 if you're not, and whether you have a university education. So, coming to UWA will actually make you more likely to be healthier or not, that kind of question. Now, so the decision is a little bit more intricate because when you just, in a standard linear regression model, you just have to pick the number of variables you want. But in this case, not only we have to pick the number of variables we want, we also have to assign those variables in a different moment. We have to have some basic information or idea about how these variables, if they're going to affect the distribution, at what level do they affect it. So again, it's more of a data exercise in this case rather than based on any sort of theory. So our decision comes down to, based on the goodness of fit and the rest of it, this is the functional form we put it down. So we have the age, actives and marrieds in the mean, and the gender. Interesting enough, actually, is the gender comes in quite strongly in the variance. We laid lambda rather than in the mean. Household income and number of children in the second moment, and the skillness and the kurtosis related parameters has employment and university education. So we estimated, and we got those are the estimates there, and they are significant. So probably have columns on the t-test there based on asymptotic normality. But instead of giving you those really boring table, what we have done when we have a meeting on this is say, well, one of us we're going to apply this result to one of us. So we're going to have a profile. And of course, Mark is upset that he's obese. I'm embarrassed because I'm overweight. So we pick Ranjon. So what Ranjon did is the covariates. He got the values of all these covariates that he has. He basically plugged the numbers in, and then he drew a nice little graph, which is the blue line. So this is his personal BMI distribution. Okay, he's in the normal range, probably because he's a lot younger than both Mark and I. But the blue line basically, and the histogram is the 2006 Hilda data on BMI. So the blue lines here is his personal range on personal distribution for BMI. So he's about 32% being normal, so he's at that 32%, which is great. He got a slightly high chance, and oh, by the way, before I move on, I'll just give you, so Ranjon is about mid-30s, early 30s. He's relatively active. He is married. He is a male. And his household income, as a poor PhD student, I'm pretty sure you know what the income is like. So he's on the low side. Now he has 2 children. So it's very admirable that he's doing his PhD with low income as having 2 children. Employment, this is the pit where he put down 1, even though technically I told him he should put down 0. He disagreed with me on that. And he definitely has a university education. So he's a rough profile, and that's the blue line that he has. But the things that's striking is that so the chances, for some reason, the chances of being underweight is really, really slim. But the chances of him being obese is actually relatively big. It's about 27%. Not as big as being overweight or normal, but it is substantially higher than being underweight. So here is the marginal effect. So the question is, based on Ranjon, he's about mid-30, early 30s. So the question comes down to what his profile will look like, right, if he ends up being in my age. So what we did is basically calculate the marginal effect and add 10 years to it. So this is the marginal differences between the 10 years. So the red line is the old blue line that you saw, and the blue line is what happened when the age was being added by about 10 units, 10 years. So you can see the changes in the shape of the distribution. All of a sudden, the chance of him being normal goes down. All of a sudden, the chance of him being underweight goes down from 6 to 3. The chances of him being overweight actually goes down too. But the good news is the chances for him being obese is actually, according to this model anyway, goes up quite significantly. So age, some reason, at least from far as the sample goes, has a really bad impacts on your obesity. So the older you are, the more likely you're going to get obese. And I hate to say it, that kind of matches up with observation. And Mark feels a lot better after seeing this because he's 10 years older than me, so he said, no, it's not my fault, it's just statistic. Right, so the next question is the household income. So there's another policymaker sort of interested sort of arena. What happened if your income increased? So he was being very ambitious. It's not really marginal impact, I must confess. He changed the income by about 50%. In no universe that fits the epsilon neighborhood, but that's a separate. So basically we're just doing this for fun. So he, again, as it turns out, it's really weird. If you increase your income, actually no, he decreased his income by 50%, my apology. And it's kind of a weird result because if you decrease your income, turns out that you're more likely to be obese. So your underweight actually goes down quite significantly, so is your normal weight. You're not going to be overweight terribly much, so that marginal impact is not. So on the overweight scale, for some reason, it's quite sticky. It doesn't change much in terms of probability. But obesity goes up again. So we're postulating, we have no evidence for this. We haven't done any further analysis. As I said, we're just doing this for fun and see how it works. Our argument, perhaps, is that if you are actually not earning terribly much, it tends to eat a lot more crap, or the food quality is probably not as good as if you can afford healthy food. To much of my horror, I didn't pay much attention to this, but to much of my horror, healthy food is actually really expensive. So we're not sure whether that was the reason. We're speculating that might be the case. Employment. which is maybe balances out with the reduction in income, because apparently if you actually do go to a job, it might mean that you're more active. I don't know. Depends on the kind of job you have. The probability of your obesity actually goes down. And where overweight, again, it stays roughly the same. But you being normal is actually a lot higher. And also, the chance for you being underweight is also high. I don't know whether, because when you have a job, you stress a lot more. It takes weight away. I don't know. But being employed is definitely good for you. So there is a very strong incentive from this result to suggest to the government, forget about the income issue, just get people a job. Okay, university education. Now, you'll be glad to know, since we all work for a university, if you have a university education, you're less likely to be obese. So the probability for that also goes down. And for you being a more normal human being, for you being in the normal range of the BMI is actually slightly higher, and you also have a slightly higher chances of being underweight. Again, for the overweight category, it doesn't seem to be what we changed. That sort of stay roughly around the same. Okay, so here is the case study, at least for Ranjon or Ranjon type person, whoever they are. Okay, so here's a conclusion. I'm not going to take up too much of your time. So we model distribution BMI using a set of covariates. As I mentioned before, this method can apply to a lot of other variables. Doesn't have to be BMI. We just thought that was particularly topical and interesting at the time. Different covariates impact different moments of the distribution. We think it's relatively low because we managed to apply and modify the MED framework. A lot more work needs to be done. We need to finish the theoretical work, and we really want to hit the panel data because when we start looking at how individuals evolve over time, there is the additional complexity with the dynamics and all the individual heterogeneity that we need to take care of. So we can't wait to get onto that, but we want to finish this one first, at least to a form where we can put it somewhere. And also, Ranjon need to finish his PhD. So that's it. And hopefully I'm roughly on time, about 35 minutes. So here you go. Thank you.
Questions? The employment effects, did you consider using different variables to reflect the different types of employment?
Yeah. No, we haven't done that. It's a good question. Unfortunately, we were limited by the data we have in Hilda. I'm not sure if it has other variables that related to the factors that employ unemployment. We can certainly look at that, but the short answer to your question, we haven't in the set that we try.
Just to follow this up, apparently you made a choice of using some of the Hilda variables and others. I remember seeing that physical exercise was part of the data that was in there.
It's active. It's just a dummy saying that whether you consider yourself active or not.
Why did you choose not to include it?
Good question. Because as it turns, it's not significant.
Sorry, because?
It's not significant. We did throw it in one of the, because we did try different combinations on that, because we were pretty blind, admittedly, we were a bit blind in terms of what should go where. We did try actives in at least the first 3 moments, and the coefficient is not significant. Now, we don't know whether that is like a multicollinearity issue, where active actually covered by, if you go to university education, you're more likely to be more active. If you have a job, you're more likely to be more active. So we don't know exactly why active doesn't come out. My guess is that that information is being covered by other variables we have in there.
So actually, that was my actual other question for you.
Yeah.
It's about multicollinearity. It's a number of variables that presumably are very strongly correlated. Did you sort of account for that?
No, short answer, we haven't, because we were a bit quick and dirty in terms of getting some results out and want to see how that will actually look like. I would admit that will give us some problem in terms of our interpretation, specifically when it comes to our marginal impact. But theoretically, if we have a strong reason to believe some of those variables are correlated, it won't cause us any problem in terms of estimation. What it will affect us will be in the estimation of the marginal impact, which if we do know they are, we have strong reason to believe they are correlated, we can account for that. Because it's essentially just deriving two sets of marginal impact and then weigh them up appropriately.
Yes, maybe just two comments. One, could you model maybe if you have the data, how commute patterns would affect the distribution of the BMI? For example, how far you from home to your workplace, you drive, or you cycle, or you walk.
Yeah.
Because that's often being discussed in this.
Yep.
And that's one thing. I mean, depending on the data. The other thing, could you, because if you have the panel, you have the time series, and then you have the cross
Individual. Yep.
Yeah. Is it easily adaptable to evaluate policy parameters?
Yeah.
Because then you can see the whole distributional impact of somehow program. Would that be
Yep. So answer your first question first. The first question is the breakdown of the variable. I guess that's also partially answers some of the other audience's question. We can, in theory, merging multiple data sets together to get those information. My understanding is in Hilder, we don't have those information in terms of whether you're riding to work as opposed to whether you're taking a car. Certainly, if we have those information available and we are looking for it, we are more than happy to put that in, because it is, I agree, it is an important differentiation.
You have very strong specific
That's right.
That's right.
That's right. So I would agree with that. We were, as I say, we were sort of limited with what we got in terms of the data set. There's a lot of observation, but in terms of the relevant question that we can use, we won't be able to get a lot of it. But my understanding is there are other data sets in Australia, certainly in the UK, that has that sort of information. So we are trying to get our hands on those, but apparently getting through those paperwork takes a bit of time. For various reasons. So we are doing that. In terms of panel data, at this stage, my optimistic guess is yes, we can, but I don't know. That's why we really want to get onto that, because we see a lot more, this method, I see a lot more possibility with the two-dimension, especially on the evolution, which is more important from my perspective than this. In fact, it's funny you mentioned that. My earlier work in this is not making the moment depends on the covariates. It's actually an autoregressive process. So my previous work in this is actually conditional on today's distribution based on yesterday. So I was actually doing the whole changes of distribution over time. So we were hoping that the panel work would be able to give me something similar to that, in addition to the effect from the covariates.
And the lifestyle of people or something like that?
Yeah, look, the lifestyle, we were limited to some sort of the consumption, how much money. I think that one of them is how much money you spend on food. I think we had that in there. I'm not sure why I didn't make it to the final model. But that's about as much of a lifestyle information I got from, or we get from the Hilder. So the short answer is no, but again, that comes back to the data issue, whether we manage to merge a substantial big data set together and get the same information out. But from what we got, the set of Hilder that we got, from memory, that to me weren't there. There's no such information available to us.
Not on genetic
No. And I think it's a bit of a hard ask, because I don't even know what my genetic makeup is. So chances are, if you ask, because Hilder is a survey data, so if you ask people that, they're not going to be able to tell you.
So in the intro of the literature, there's the reading that says the outcome depends on the probability space. So do you have an insight how you decide on the probability that you use to compute your outcomes?
Well, okay. I'm hoping I understand your question correctly, because that's the probability, that's the distribution.
I guess the question I'm trying is your assumption, you do the maximum likelihood optimization to try to get a hand on those parameters. What's behind that, and how you have that model lambda as a function of the parameters or the covariates, and what's the underlying assumption you use for that maximum likelihood optimization? Is that the question? Yeah.
So do you have these lambdas for every observation or every person?
Oh, no, lambda, no. Okay, right. So yes, lambda is individual specific. So all we're doing is saying that the lambda as a parameters changes depending on the covariates. And so if you're looking at this beta xi is your lambda. Right, so that controlling the shape of the distribution at the individual level, and that control, that determinants of the shape and the scale and the whatever, is based on the covariates, your incomes and your unemployments, the rest of it that goes in. So what we're doing here in that case is just estimating the beta. So it's the marginal effects, if you will, part of the marginal effects.
And Y is your BMI, right?
Sorry?
Y is your BMI?
Y is our BMI, yes.
Yeah, okay. So at the end of the day, if you get rid of the moment conditions, you have like this density function, right?
Yep.
What are you gaining by using the entropy measure method as opposed to the maximum likelihood?
Oh, no, okay, right.
The distribution looks like a nice distribution, right?
Yeah, okay. Look, yes. The introduction, well, the short answer is nothing. We don't actually, we can't turn around and say, we're just estimating this. We don't have to mention entropy at all.
Okay, so you could argue some function like gamma or even one. Yeah, okay.
Yeah, it's just that we did the entropy spiel because we want people to be able to see the connection between the what we got in the lambda, or in some sense in the beta and the x, with the moments of the distribution. It's just a nice little link between the two that we can immediately do without going through too much mathematics behind it. But in general, and also provide some form of justification why we chose the exponential function rather than a gamma or whatever, or the log normal for that matter. But in a nutshell, in practice, yes, I agree. You can just put that down and say, this is this density we want to use, and this is the beta I try to estimate, and we can back out the moment the usual manner, and be done with it. That is certainly true. But we're trying to tell a story in terms of justifying the choice that we make, which we were asked to do many times when we try to write a paper.